introduce Irena Lasiecka. She's affiliated to the University of Memphis, where she has the position of distinguished professor. Her research includes nonlinear PDs, optimization and control theory, dynamical systems, and numerical analysis. Let's watch her exposition about long-time behavior in flow structure interactions.
Okay, thank you very much for a very kind invitation. I'm glad to be here in this fantastic Brazilian meeting. Okay, I see so many friends. So what I would like to do a little bit, to introduce a topic of which is motivated by applications to flow structure interaction. And first of all, I would like to acknowledge several of my collaborators. So I just put here in alphabetic order. I would like to mention that Igor Chueshov was my collaborator for more than 10 years. Unfortunately, he passed away, but there is a lot of work which was influenced by his research. Erdowell is from Duke University. He comes more from the engineering side and was giving a lot of impetus in terms of a model, in terms of experiments, and to tell us what is reasonable mathematically or what is not. Most recent work is with Denis Bonner and Filippo Gazzola and Justin Webster, which relates to some of the problems of a flow structure interaction is related to the collapse of Tacoma Bridge. So we're trying to understand why it collapsed. I also want to acknowledge support from National Science Foundation as well as MSRI at Berkeley, which is right now, there's a program on mathematical theory of fluid dynamics. So part of this work was done during this semester. Okay. So first of all, talking about flow structure interaction, why we are interested, because it has a lot of application. And the main problem is control of flutter. What is flutter? Flutter are sustained oscillations. Okay, so I was just talking about applications of a flow structure interaction and control of flutter in particular. And you can see that the flutter can be really damaging in terms of the consequences on a material because you have a structure which is related to some material properties. And the model or the properties very much depends on the velocity of the flow, because the flutter is connected with a flow that impacts the structure, and velocity can be subsonic, supersonic, or transonic. These are the basic three regimes. More recently, the control of flutter finds a lot of application in medical sciences. For example, you have a fluttering arteries, which is related to cardiovascular disease, as that's exactly the model of interest, or in a treatment of apnea. In engineering, there are millions of applications which starts with bridges and buildings, yeah? So it's fluttering structures, and also damage which is caused by flows in flexible pipes. In nuclear engineering, when you have a heat exchanger vanes, and also on a positive side, most recently we take advantage of harvesting of flutter. So flutter is a good guy because it can be converted into the energy, like windmills. So that should motivate really the study. So here are some examples of a flow structure interaction at the supersonic level. So you have a jet which is surrounded by the flow, and this flow interacts with the surface. Okay. On the subsonic level, we have a Tacoma Bridge, about collapse in 46, when the flutter wind really caused a rupture. This is an example of treatment of apnea. When you look at the intake of the air into the facial palate, which creates an oscillation of the facial membrane and can lead to choking or other tragic consequences. So in this talk, I will try to be quite qualitative but at the same time, I would like to show some new areas of mathematics which to study this kind of problem. So we start, of course, with some PDE models. And what I want to particularly emphasize, because we spent a lot of time on this, role of modeling, because sometimes doing mathematics, we put various terms in the equation, and we are happy that we can have a theorem at the end. But then working with people who are closer to real life, like, for example, engineers with understanding of mathematics, we can see that this model really does not models the particular phenomena that we try to describe. So yeah, I will give you a very simple example how one can prove that the model is wrong. So many people work on this model for 20 years or so. And then I go to the main result. So main result will be representation of the whole system, which is a coupling between flow and the structure, the dynamical system, and lead to the study of long-time behavior and questions such as like attractors. Attractors, of course, only for the structure are possible because you cannot control the flow around you, but you can control the flutter as impacting the structure. I give you some ideas about the proof, and we will move to conclusions, open problems. Okay, so the basic model is the one fact I spoke many times before, because this is a long project and really a lot of things have been rediscovered recently, but we started a long time ago. So you have a thin plate, which I call omega, and this is immersed in the flow of which moves with a velocity u in the negative direction of x. So the whole game is the flow affecting the structure and inducing oscillation. Of course, what is important here is the pressure of the flow. Okay, this is a force that acts on the structure, and that's what we want to model. And we have a vibrations, oscillations of the structure. Now, by phi, I mean velocity potential of the flow, and by u, it's a vertical displacement. Okay, so we have a three-dimensional couples two-dimensional model. So we have here also example. So what we are trying to do, first of all, you ask a question whether you can eliminate flutter if it is possible. And the answer would be in some cases yes, but in general not. But then you can control a flutter speed. So the speed which allows you to live without the flutter. And that's a very practical question, but mathematically it's pretty involved, because where your control is supposed to act, obviously on the structure, it cannot affect the flow itself. Okay, you have no control. Because the flutter, again, I remind you, sustain oscillations and can lead to damage or breakage. And this is really a fundamental problem in applied sciences. Okay, so let me just go through a very, very quick derivation of the model, just to give you an idea how it is connected with the flows and with nonlinear Euler equation. Because what we start with a flow of gas, because it's essentially what you have to look, and inviscid. So we don't take viscosity because that's what the model is in 3 dimensions. Okay, so we have a conservation of mass equation when rho it's a usual density. And v, it's a velocity of the flow, and the conservation of momentum, which is a classical Navier-Stokes equation that you are familiar with. Okay, and p, it's a pressure. The structure is modeled by the nonlinear, and I here heavily emphasize it's necessary to have the nonlinear term, nonlinear plate equation, which is activated by the pressure coming from the gas. So P, it's a pressure coming from the gas, and that's exactly what creates our flutter. Okay, because it's an interaction between flow and structure. And there is a nonlinear term here, which is important. We take here von Karman because it's sludge displacement model, but can be also some other models. But von Karman is pretty good in terms of reproducing the effects. And we have this nonlinearity in the structure, which is absolutely critical because everything what I'm going to say is not true for linearization. Okay. So this is not a linearization. And here I put this parameter gamma, which corresponds to the rotational inertia for the plate. And point I want to make very quickly is that this gamma has to be equal 0. That if we take gamma non 0, it would help mathematics tremendously, but it's going to destroy really what we are trying to prove. Okay. So this is a model, and what you do. We linearize this only flow around an unstable profile. So we assume that there's a flow with a velocity capital U, and this capital U, if it's subsonic, so will be below 1. After, of course, normalization, if supersonic, will be above 1. And we assume that flow is irrotational, so which means that the velocity can be represented as a gradient of some potential function, and also barotropic. So we have a state equation which relates linearly pressure and density, and of course flows inviscid. So if you introduce the set the setup to the equation. So we have here density equation linearized around this unstable flow, because that's important. This parameter capital U is critical because that's what causes instability. And then we apply this transport term, because this is like a material derivative, to the Navier-Stokes equation. And we do some calculations. Okay, so I have here, on both equations, and what we end up with equation for our elastic potential, and what it is nothing else but material derivative of the flow, and velocity of the flow is a gradient of this potential function. And that's a really main player, elastic potential, because that's what impacts the structure and causes instability. Okay, if capital U is 0, then problem is dissipative and there is nothing to be. Okay, there is something to be said, but main problem is precisely caused by capital U not equal to 0. And then we obtain the following hyperbolic system to study. Okay, after linearization. So you see here two variables, elastic potential and also gradient function phi. And on a structure, we have as before. Okay, I keep this parameter gamma, which eventually will have to be 0, and it's forced by this elastic potential. So this is the bad guy that is causing instability to the structure, okay, the red guy. What is very important are boundary conditions, because you have to connect the flow to the structure in a certain way. And there are a variety of boundary conditions, and depending on the application, you have to decide which one you want to work with. But most importantly, the mathematical treatment is so different and really involves different almost areas of mathematics or harmonic analysis, depending on boundary condition. So there is a first boundary condition, which is called flow tangency, which is a classical Neumann type of boundary condition, which essentially imposes that normal derivative for the flow is equal to this material derivative of a structure applied to the structure on omega, on the structure, and 0 outside, okay? And there is another boundary condition for the flow, which is referred as Kuta-Yukovsky, and that is the first one on omega is exactly the same, it's a Neumann. However, outside the flow, you have a 0, but 0 is imposed on an elastic potential. So this is a very serious mixed boundary problem that you will see that just to get a solver or to get any sort of a theory for this involves the tools of so-called inverse Risch transform. Okay, we'll see in a moment. So these are two types of boundary conditions. For the structure, you have a usual, either you take a clamp, you can take free or hinge or combination of the two. Now, in terms of application, if I study a bridge, okay, collapse of a bridge, so what I'll be doing, I will take a flow will be Neumann, tangency Neumann, and structure will be free combined with hinged, because you have one side which is free and say lateral side, the shorter side of a bridge will be hinged. For the flag, fluttering in the air, for example, that's a good example. You take a flow which is Neumann, but structure will have to be free and clamped. Free boundary conditions do provide, interesting events. Oscillating panel, in some sense, is the simplest, because we thought that's what we have been studying in the past. Probably heard my talks about that. It's a flow is just a Neumann boundary condition, and structure is clamped. The wing of aeroplane, in other cases, you have a flow which is a Kuta-Yukovsky boundary condition, because what it means is that outside the structure you have a drop of a pressure. That's exactly what creates a lift on your wing. Okay, so it's very important. And that's Kuta-Yukovsky, and structure itself will be free or hinged. So these are type of boundary conditions that you would like that you want to consider. So what are the questions that you would like to address in context of this problem? So of course you want to have a solution, so well-posedness of equations. So I'm going to discuss this in a moment. But from the point of view of a control theory, we were guided by experiments which were performed at NASA and Air Force Lab at UCLA and also at Duke University. and they show some stabilizing effect of the flow on the structure. I'm saying stabilizing in a quotation mark because it's not really stabilizing like in Marcello talk that you have a stabilizing function. There is nothing like that because we are not going to have any dissipation directly, because model has no active dissipation, whether on a structure or the flow. The only source of dissipation will be a little bit of dispersion, but there is no dissipation. However, guided by this experiment, you would like to show that there is a stabilizing effect. And what does it mean? What does it stabilize? So here, guided by this experiment, we'll be studying the following question. First of all, generation of a nonlinear evolution in a finite energy space. And here, finite energy space, it's a classical space related to the velocity, to the flow, and to the structure. So you know what it is. And also to show uniform attraction of structural evolution to a finite dimensional set. So we'll show that eventually this problem will be reduced to some finite dimensional structure that you can do something about, but this is only on the structure, not on the flow. You cannot control on the flow. You cannot negotiate with the flow that is in R3+. And then in some cases, in the case of subsonic flow, we'll be able to show strong stability to equilibria. And once you have a finite dimensional structure, you can think of a finite dimensional control theory, which can implement some strategies on controlling. What I want to say, what has been known, okay, because the problem has been studied for a long time. What has been known that, first of all, okay, where I have this. The problems were considered for so-called rotational inertia. So there is this gamma positive. So you know that this induces one extra derivative, okay? And the flow is exactly like the same equations that we have in the subsonic case. And then what happened, one can show in this case that there exists global unique weak solution, okay? And space in which you are having the solution corresponds to the flow, which is a flow function plus elastic potential, which is H1, L2, and the plate equation H2, H1, YH1, because we take gamma positive, okay? And there are here, I have listed a lot of work. Some of them are even you know, very, very recent, by Marianna Schubo, but they relate to the linear structure. However, this work, while they pertain to well-posedness in the spaces, there is no word about stabilizing effect of the flow. Okay, so there was no, this model does not exhibit stabilizing effect. And now question is why? Why can we understand that the model is wrong? So why it's not possible to have a stabilizing effect of the flow? And here I want to argue that if I take gamma positive, which is a very nice mathematical thing to do because nonlinearity becomes subcritical and a lot of good things happen, I cannot possibly think of a stabilizing effect of the flow on the structure. So how do we argue? By doing some calculations, and that was done some time ago with my joint work with Chuyeshow in a book, in fact, that you start with a plate equation subjected to the force induced by elastic potential. And then you solve explicitly for the linearized equation for the flow. You can see that really this elastic potential for time t large enough, not for small time. This model is not correct for small time, so would not help you in studying well-posedness. But this can be elastic potential can be represented by the quantity depending only on U itself. Okay, so you have exactly the same material derivative but applied to U, and there is a term Q which is a delay term. Delay term is pretty not very friendly because her second derivative is not a lower order term, okay? So we have a delay term and we have material derivative acting on the structure. And now, okay, so I want to make a quick point, okay, why there is no possibility of showing has a stabilizing effect when gamma is positive. Because you see that the flow itself does contribute a good guy, and good guy is this U sub t because you put to the left. Okay, so you know that this has some stabilizing effect. Okay, and this instead capital U, which is exactly velocity of the flow, it completely destabilizes, plus the latent destabilizes. So the question is, how good is the stabilizing effect? And you see that if I consider rotational forces, this guy here does not stabilize a rotational model. Okay, you will have to put some what is called structural damping, which is Laplacian ut, in the model to get really linear part somehow exponentially stable. That's what you will need, and that is not possible simply. So there is no hope to get some evidence, okay, mathematical evidence of stabilizing by the flow by working with rotational model. Okay, so that's why the papers that I mentioned, they introduce structural damping, and then they can prove things, more friendly. But this is not, flow does not contribute to the structural damping, okay? Because flow provides only the pressure that is exactly the term which I have here. So this should be, so in fact, when you take a gamma equals 0, then it's clear what the gain, at least in terms of asymptotic for the structure, is that you have some stabilizing effect on the structure produced by the flow, but you have a huge amount of destabilizer. So there is no dissipation, system has no dissipation. You don't have a nice term, you don't have a nice energy relation, you don't have essentially anything. But you have a nonlinearity, which is important here for the work. So we need to take gamma equals 0, okay? So I go back to the model. So the model that we study, that's very important. It's exactly the plate equation with nonlinearity, which is of cubic type, with a pressure coming from the flow. This is the same element. And I'm here taking clamp boundary condition because these are the simplest, and I want to guide you what kind of a analysis will be involved. An elastic potential is exactly this material derivative applied to the flow. So this is a plate equation. Okay, plate equation has this, it's driven, it's forced by the flow. And flow equation is this hyperbolic system, and I'm here first considering Neumann tangency boundary conditions. So it's a Neumann boundary conditions at z equals 0 at the bottom on gamma, which is material derivative of the structure. Okay, that's what induces the flow, and we have also outside omega here. I take at the beginning a normal derivative equal to 0. So we have two players. This elastic potential affects the structure, and so-called downwash ignites the flow because this is a forcing term, force applied to the flow. So it provides perturbation of the flow itself. Here I want to say that important is the nonlinearity, it's cubic, and we consider von Karman nonlinearity. So this is defined by so-called Airy stress function, which is a biharmonic solver of a von Karman bracket. Von Karman bracket is defined by taking products of two derivatives. Okay, so it's a really L1 function here. If you think about it, it's L1 function because if I take H2 functions for you, so you take a two derivatives, so this is L1 function. And in fact, the regularity of Airy stress function, it's a very important here ingredient in the analysis because if you just look at the equation, you have to solve by harmonic with L1 function. However, joint work with Daniel Tataru several years ago, we were able to show that in fact, this Airy stress function has a regularity due to compensation compactness of the type of the W2 infinity, which means the second derivative of Airy stress function is a multiplier. Okay, so that is very important for what nothing will be possible to prove without this information. And that's based on some Pierre Williams, Kaufman-Meyer compensated compactness method. Okay, so you have a model, and we know that gamma has to be equal 0. And we have a criticality of the nonlinear term on the structure, and we'll be studying well-posedness of finite energy solutions and long-time behavior. Okay, so based on experimental studies, we would like to show that the flutter can be eliminated on the subsonic level. Okay, so it means the control should be able to do this. But in general, we will be able to show, we would like to be able to show that the whole dynamical system is reduced to a finite dimensional attracting set on the structure only. Okay, the set is pretty bad, it's chaotic. So, however, dispersion provides some stabilizing effect, because otherwise you cannot hope of any sort of attractor. So you have to somehow be able to put your hands on the stabilizing effect and quantize. And I want to mention that most recent work with Denise Bonner and Gazzola is really related to what happened on this finite dimensional attractor, and it is can be quite complex. It's finite dimensional, but nevertheless consists of a oscillating or limit cycle periodic trajectory. So we do have a flutter on the finite dimensional set. So the question will be, of course, how to eliminate. But we have a good description what happened asymptotically. So what are the mathematical challenges? Lack of active dissipation on both flow and structure, and we have a couple. Okay, lack of compactness and regularity. And this, you know that this is critical, particularly when you study long-time behavior. Compactness and dissipation are two things that you need to put your hands on. And this is due to exactly this loss of one derivative because of the modeling. You cannot take rotational forces. And then nonlinear term becomes critical at this level. And there is also potential degeneracy of the flow of the energy, potential energy. So these are the issues to contend with. Now, in order to understand a little bit what's going on mathematically, let's look at the energies, because that will be something that everybody will get started with. Yeah? You multiply by something, you integrate by parts, and you see what happened. And that, of course, has been done as a first step. And if you take a plate equation, then you get an energy, which is kinetic plus potential, it's nonlinear energy, which is here. As you see, that nonlinear energy might not be necessarily positive. But here it's exactly a role of nonlinearity, which allows you to show that it doesn't go to black hole that is bounded from below. So I want to anticipate this. It's very important. That's why everything what I said without nonlinear effects would be really false, because we will not have even starting point. However, the flow equation, flow energy, has a term, you know, also kinetic, but potential energy has this minus sign with u squared. If u is greater than 1, this quantity becomes negative. So it does not provide any topological information on the flow, okay? So you have to see that the problem is when u is equal 1 or greater than 1, then you cannot say that energy generated by the flow gives you any sort of a decent norm. And there is interactive energy between plate and flow, and this is given by the boundary term. And this term, of course, is activated by the flow itself, by this capital U. But in terms of a topology, this is not a bad thing, because phi is in H1, so trace is well defined, and UX is also well defined. Okay, so interactive energy, it's a good term. So flow energy has no sign, so it can be negative. But what happens is that everything adapts to constant. So what we have here, we have a conservation of energy, but energy that has no topological information. Okay, so this you cannot. Everything is hidden behind the structure. So any sort of an energy type of argument or techniques, Galerkin, whatever you want, is not going to provide you information. Okay. So as I said, we have a balance of energy, but we don't have dissipation, and we have loss of ellipticity. So I already said this thing, so we don't have to worry about it. Okay, so what do we know up to now? Flow does not stabilize rotational model. That is confirmed by the experiment, so we work with a gamma equals 0. Okay, rotational model was great for mathematics because it was providing an extra derivative. It's good for compactness, it's good for nonlinear terms, which becomes subcritical, but it's not physical. Instead, the original model brings about new mathematics, which is handling of a nonlinear term, okay, which becomes critical. And we know that any sort of a study of dynamical system with nonlinearity, which is critical, requires always some ad hoc calculations, because you have to show asymptotic compactness at some point. We don't have a dissipation, and of course we don't have a gradient structure, just because even this lower order term destroys. In addition, we have a delay which has a principal part of operator. It has the stabilizing effect. So we have a lack of compactness and regularity. So what are the new techniques that you need to really rely on? This is mostly harmonic and microlocal analysis, as you will see, and dynamical system for non-dissipative systems. Okay, it's important because there are a lot of references for dissipative dynamical system, but essentially there are very few results on non-dissipative because the energy or Lyapunov function simply in a standard form does not work. Okay, and this is contribution also of my co-author Chuyeshov. We have several results in our book. So here I just give you overview of the results, so at least you know so what we can prove. We can prove existence and Hadamard-Well posters of finite energy solution for a whole thing. We can show that solutions are bounded for all times, and here just because there's no linearity in the plate, otherwise would be false for linearization. In the subsonic case, we can control with a feedback, okay, on the structure, and we can stabilize. So it means that we can drive the solution to the stationary state. So it means that flutter can be eliminated, as that's what was noticed, okay, by the engineers. And this result is only for the clamp boundary condition. For the free boundary condition, you cannot stabilize. But for any velocity which is different than 1, when you have a flow data compactly supported, all weak solution without any dissipation converge to a finite dimensional and smooth cess. So it means the structural dynamics becomes finite dimensional asymptotically. So this is a qualitative statement of result. And here there are theorems on the generation of nonlinear semigroups. So we can construct dynamical system on a space H, which is a classical finite energy space. For the structure, you have H2L2. For the flow, H1L2. Semigroup is bounded, and also for smooth initial data, we have a smooth solutions. Okay. I have to say that there was some earlier work by Buttedimon-Welf, Chuyeshov, published for subsonic case, but only for a smooth data. So it was not a finite energy solutions, even in a subsonic case. Here, this thing works for every year. Now, finite dimensional attracting set. Here's a statement. It's a joint work with Chuyeshov and Webster. And there is a good exposition in Oberwolfach seminars. There's a book that was published by Oberwolfach. So we had the lectures for 1 week on the topic, which says that solution is that if you consider structure plate equation only, and you take a finite energy solution, so they converge uniformly to the attracting set, and set it's in fact has one derivative more, so it's smooth and has finite fractal dimension. For the initial data of the flow, which are compactly supported, but that is natural. Now, what is important that this attracting set, and that's the main interest, what happens once they're in that set, can be chaotic, has limit cycles and periodic orbits. As it also is exhibited in our recent work with Denis Bonner-Gazola, which is going to be published this year in Annals of IHP. Now, if we take subsonic case only and you provide some damping, okay, here there is a damping on a structure, it can be shown the whole system, which means structure and the flow, the whole dynamical system, converges to stationary sets. Okay, that means that flutter can be eliminated at the subsonic level with a control, with some damping, which acts on the star. Here we assume that damping is not localized. Whether it can be localized, it's a very, very difficult problem. Also because the proof of the strong stability, which looks in a sense normally in the dynamical systems, this is the first problem, the simplest one, but not because of lack of dissipation. It's not, and eventually it really relies on a much stronger result, which is uniform convergence to attractor of the structure. Okay, so this is in fact the probably most difficult. Now here I want to show you some pictures, okay, which are obtained by studying numerical, doing numerical simulation. So you can see what can happen that you have once you have on a structure that solution oscillates, has a flutter, but eventually converges to some steady state, but you have a several steady state, you have a multiple solutions. However, we're able to show that this that generically there will be finitely many, which is also important. Okay, so you have this kind of situation, but also you can have a situation that you have oscillation at the beginning. Okay, here it's a convergence. They diminish, but they never really die out. So there's kind of a, still they will be sustained, but at a reduced level. But this is result of the control. Okay, result of a control in case of a free boundary condition. We cannot show that goes to equilibria, but goes to a certain epsilon neighborhood of equilibria. In a case of a supersonic or free boundary conditions, what is happening, like a Tacoma bridge, if you don't do anything, then oscillation remain in fact at a certain amplitude level. Okay, so we don't without any control, you have precisely here chaotic type of behavior, and there are sustained oscillations. Okay, like here. Okay, so in the beginning they are probably more rapid, but then they kind of stabilize, but stabilize to sustain oscillations. So this is a flutter. Okay, so now let me just say a few things about, yeah, I started 10:02, yeah, about the proof. Okay, I don't know how far I can go because I have a lot of things, but at least I would like to give you some ideas about techniques used. So you saw this slide about energy. Energy doesn't, it looks nice, everything is constant, but doesn't tell you anything. So we have to do some different look is needed. And in fact, in the supersonic, in every case, and particularly in Kuta-Yukovsky case, when you have this mixed problem, when different quantities are defined on the boundary, essentially oblique problem, we introduce a different type of energy. Energy of the plate is the same. However, energy of the flow involves, in fact, the main protagonist, which is elastic potential, plus a gradient of the flow itself. Okay. Okay. So kinetic energy is hidden here in a elastic potential, which is a material derivative of the flow phi. And now what happened? So what did we gain? We gain that we have a good topological quantities for the flow. So this is L2 and this will be H1. So it's exactly what you want. So energy of the flow is perfect. Energy of a plate is as before, and we hope here that nonlinearity is going to somehow prevent us going to the black hole, which we show is related to maximum principle for Monge-Ampère equation for that matter. As this result. But then we write energy balance. Energy balance is now formally, we have a propagating integral, which depends exactly on velocity of the flow u. And what it is here under the integrand, you have a trace of the elastic potential. And remember, elastic potential is defined only in L2, so this trace, you don't have L2 function. So you have to worry about times the structural quantity, which is well defined, okay? So the thing is that we have to somehow live with this propagating integral. Now, what is bad about that? What is a concern? That first of all, for well-posedness, you have to do something. You have to find independent results, that allow you to get some bounds on this and construct solution. And for dissipation, for long-time behavior, it's even worse because there is no even sign of any sort of a dissipation because you don't have a control of this quantity. It has no sign and it's not even well defined. However, here we are in a situation that we have good energy, but we have a bad energy balance, and we work with this kind of a scenario. So we know where to concentrate our attention flow in information about the behavior of the pressure, because this elastic potential is a pressure exercise on the structure. It's traced to the boundary. It's critical. Okay, so that's what we need to really have some information on. Okay, that leads us to the problem that we do have some experience because we have a Neumann problem. So we know that in 2 or 3 dimensions we don't have a Opatinsky condition, so we don't have a good regularity for a solver, for the hyperbolic Neumann solver. And as we know here, just recall that if you consider just the wave equation, which has H1 solution, is driven by L2 log, forcing term, a normal derivative is in L2, which we have here, then what you end up really with a solution on the boundary. So Dirichlet trace is no longer H1 like would be in a hidden regularity case, scenario, but you have a time derivative in negative space. So it's clear that the potential, this elastic potential is not going to be to function on the boundary. So this is a famous problem and very good analysis is in the paper by Tataru in 98 for just a wave equation, but that's a very good guide. So we have to somehow account for the difficulty of a definition of elastic potential on the boundary. And the nonlinearity becomes critical because we have only velocity of the structure in L2. So we don't have any room for extra regularity. So what we need to study, we need to study first the trace of elastic potential, and that is related to this hyperbolic system. And for the structure, we have to also find the trace for the solution. And then we have to construct the solution, and construction will be based on an approximation of a domain of a hyperbolic generator. The reason is that here, even if you take a Laplace transform or whatever for linear problem, just forget about nonlinear. If you take a Laplace transform, then you will see that you don't have the usual, gain of ellipticity like for wave equation. But we have really hyperbolic things. So we have to, domain of a generator is not smoother. So we have to allow you to do calculation. So we have to provide definitely some approximation procedure, but that's a technical part, okay? And here I would like to mention to start exactly with this hidden regularity for hyperbolic Neumann-Dirichlet map. Why? Okay, so what we are doing, we are taking the Lambertian, but perturbed by this capital U. So the principal part is perturbed, okay? And we are taking finite energy solution, okay? Such that the normal derivative of that flow is in L2. And we are looking at the elastic potential, which is material derivative applied to phi, which in a sense, this is a tangential derivative of phi, okay? So you feed normal derivative L2, and we are looking at the tangential derivative, tangential in time and space of the same quantity, okay? And here what we can prove that this results in a loss of 1/2 derivative on the structure. And that is going to be something that we will be able to work with. So this is one result that is obtained, and there is another result, in fact, by looking a little bit closer, that's the most recent result, just by realizing that I'm not taking just arbitrary Neumann data in L2, but I'm taking material derivative of the structure. So this is a special element, which is also only L2, doesn't have an extra regularity. But in this case, by looking by structural information on the structure of this data, we can show that in fact, the elastic potential is in L2. So we are essentially, we have a result like Wapatinsky condition would be holding, but only for the data which are fed by the structure. So really for our problem. So it's not a generic, but just for that problem. And that's very important to understand where is the magic, where is the compensation, why does it happen? In some sense, physics tells us, okay, things have to be better than what you can really compute mathematically. And that's exactly what we discovered. Now we'll explain this in a moment, and it has to do really with a problem of studying regularity of the Neumann to Dirichlet map for hyperbolic problem, for hyperbolic Neumann-Dirichlet map in anisotropic, use anisotropic regularity. So what you have here, if you take regularity in the whole set, omega, that is too brutal in a sense. You have to really split and look at the anisotropic level. And I would say that the precursor of this kind of approach was Tataru many years ago, because in his paper in Analisi di Scuola Normale in 98, he has a result on anisotropic regularity. What happened with the solution when the data anisotropically, so microlocally, has some better regularity in some sectors. And at the time we're saying, okay, that's a crazy type of stuff to look at it, because when do you know, how do you know that you have this kind of results? But mathematically was very beautiful based on symplectic geometry. And here it's a really very real problem coming from the flow structure interaction, when we cannot really quote Tataru result, but we can use some of the techniques. When you have exactly the situation that the type of interaction between structure and the flow, it leads you to necessity of looking at anisotropic regularity of a Neumann-Dirichlet map, okay? And what is the basic idea here, as usual, for hidden regularity for when Łopatynski condition fails? The usual idea is you simply look at the tangential operator, and because it's on a boundary, and you are micro-localizing into elliptic sector, and this is hyperbolic sector when Łopatynski condition holds, so you have a dominancy of the time derivative in a sense. And then you have a characteristic sector. This is exactly what Marcello was talking about propagation. It's a characteristic sector. And here is the loss of a differentiability of a Neumann to Dirichlet map, typically for wave equation. So the idea is very simple. So if I have a data which only here have improved regularity, okay, in such a way to match regularity which is achieved in other two sectors, and this is according to the hyperbolic theory, so we know what it is, then we are done. So idea it's kind of natural, but implementation, of course, involves a lot of cutoffs and commutators and symplectic geometry, really, okay? But we are able to do it. So we are able to obtain this result for a combination of a structure. And then here, just as a reminder that what is very important to have a good understanding of nonlinearity, because our plate equation, it's forced by this elastic potential, but also has this nonlinear term, which is driven by Airy stress function. And having here results that Airy stress function has this additional unexpected regularity instead of being, say, H3 minus epsilon, that would be a classical result due to Lyons, but then would give you a bracket in a negative space, so you cannot even multiply by function with L2 and have a quantity which is finite. So the first attempt was to think whether we can improve differentiability, and that is not possible. In fact, one cannot show that it's above 3. Which will be enough for Sobolev embeddings. Instead, one can show that this regularity of Airy stress function is W to infinity, as it involves Hardy spaces, type of compensated compactness method. So this is a result which also goes to joint work with Tataru, but it's very critical here. Okay, so what I would like to do, I have so essentially this result of special regularity for the wave equation, for the perturbed wave equation, and an expected combination that the structure provides you this geotrophic regularity, plus some methods which were introduced with Tuyeshev and Webster. It was already in 2016. A general strategy how to deal with the system plus this regularity gives you well-posedness for the case when you have a Neumann tangency boundary condition. Neumann meaning that boundary conditions are really given by Neumann. Yeah, by Neumann traces are signed. This is either 0 or the downwash coming from the structure. Now I would like to save a few minutes and to tell you what happened for Kuta-Yukovsky boundary condition. So that's a different problem, and I think that it's interesting to see how different type of mathematical tools if you just change this boundary condition. So what is a Kuta-Yukovsky? That's a very famous type of boundary condition. So what is happening? We are looking again at the same structural equation driven by this pressure or elastic potential coming from the flow, and we consider, say, let's take a clamp boundary conditional structure. It's not essential, and this is equation for the flow. And what are Kuta-Yukovsky boundary conditions are such that normal derivative restricted to omega to this plate is as before, is driven by the structure. However, outside omega, we don't have information on the normal, but we have information that material derivative of the flow is 0. So our elastic potential is 0. And what is happening physically, that there is a jump really of the pressure exactly on the boundary of omega, which provides a force for the wing or for the plane to lift, to fly. Okay, so that is very, very important thing. But boundary conditions are of a mixed type. Okay, you don't have a Neumann equals to whatever it is, but you have a combination. So what do you do with a case like that? So first thing what I want to say is that we again, if once we have a good hidden trace condition for this kind of a configuration, then we are in a business with a general theory because we have a template to follow. So what will be the result exactly here? The result that we want to prove, okay, here I'm postulating hidden trace condition. So if we have this condition satisfied, then we can do the rest. So what the condition is, we have a normal derivative in L2 as before. We have some initial data of the flow. And here what we would like to have, we would like to have an elastic potential, which is tangential derivative of the flow. So think of it, this is normal and this is tangential time and space, but measured only in a -1/2 minus epsilon. There is an additional epsilon here. And that is enough for us to really engage in the template for proving well-posedness, generation of solutions. So this is just written that you see tangential derivative. So the map from the normal L2 into the tangential, okay, for this hyperbolic system is allowed to lose 1/2 plus something derivative, okay. This is more than a classical wave equation, which according to Tatar, the optimal loss is 1/3, okay. But here we are losing more because of the this element capital U. And different problem, of course. So in fact, as I said, that if we assume this hidden trace conditions, then we get the solutions in a finite energy space, okay? So the question is, how do I prove this trace condition? And here's the tool, it's a finite Hilbert-Risch transform. And there is a recent paper that I want to advertise, it's published in Annali Mathematica Pura Applicata, inversion and extension of finite Hilbert transform by Kubera, Okada, and Ricker. In fact, this problem of inverting finite Hilbert transform goes back to trichotomy. However, we need to go much beyond the classical treatment. Okay, so how do we prove this kind of thing? Remember that the microlocal analysis dividing into sectors and all the things was good when we have a normal derivative defined on the whole boundary, so omega and outside. Now, if I don't have this, I have to have information either on normal derivative outside omega or elastic potential on omega, either way. But I have to have a consistent quantity which is defined on the whole boundary. So what do? We started beginning something that is quite, natural. That means that we take a Fourier tangential time Fourier transform. So I don't go here to the details for the waiver. So we just see. I just want to tell you. So what do we obtain? We obtain the following relation. This Hertz means Fourier tangential Fourier Laplace transform. Time is a Laplace and space is tangential. So you see. So what we obtain the following relation, that we can find a normal derivative of the flow of Fourier transform defined in terms of the elastic potential, which is here, via certain pseudo differential operator, which has here a symbol. The symbol is related again to the Neumann solver, but I don't want right now to go into details. I want to tell you about the properties. So if we can solve somehow this equation, so essentially give a relation, if I have a full information on elastic potential, I get a normal derivative. And if I can invert this operator here, I can go all the way up. And that's essentially deals with a basic problem from the very beginning, that normal derivative, it's prescribed, it's given on omega, but the outside of omega, we have only given elastic potential. So we have to use this information into that formula. We have to, and then, okay, if I call script n is a pseudo differential operator associated with this symbol m, which was square root of d, which is a hyperbolic solver divided by tangential derivative, time and space. So we get a very simply looking equation of the following type. That this d it's equal projection on omega of that operator m, okay, pseudo differential applied to the psi. And what I want a psi, because I want psi on omega. I have a psi outside omega equals 0, but I want a psi on omega. So I want to find psi in terms of a d, okay? And I have a symbol of this operator m, such as the Fourier transform corresponds to exactly this quantity. And now how finite Hilbert transform comes to picture. It comes to picture that I have a projection in front, okay? So what we know only, we have this D, which is defined only on omega. And that's why finiteness, that was first, I would say that credit should be given to Balakrishnan many years ago, because he made in fact, he spoke even with Terence Tao to find out more information on finite Hilbert transform, but he made this correlations that finite Hilbert transform do enter the picture. So what are finite Hilbert transform? It's nothing else but classical, you take a classical Hilbert transform, but you truncate, say, to -1,1 just for simplicity. So it's a principal value. However, what are the properties of this finite Hilbert transform? You know that Hilbert transform itself, it's an isomorphism on LP for any P between 1 and infinity excluded. Now, finite Hilbert transform is bounded on LPs, but it's not invertible. It's not invertible. In fact, if you take P equal 2, which is the nicest case, it has a dense range, so inverse is not continuous. For P less than 2, it's a Fredholm operator. These are the results which are known. So what we are endowing here, you see, we have the symbol which is projection on omega times this operator M. So we want to exhibit this finite, hereby will be finite Risch transform from this symbol, okay? So we can define finite Hilbert transform, Risch transform as a projection of a regular transform times extension by 0, because this has to work only from a bounded to a bounded set, okay? So this will be the symbol. And now the key observation is that this operator coming from the calculation can be written as a product of a Hilbert transform times something, some other operator that is related to also to the solver of the wave. And this is an operator that is going to lose some of the derivatives, but we have a specific representation. And that would lead us to the following equation to study. Given D on omega, find psi on omega only, because outside omega is 0, such that this operator here gives you D. Okay, so you have to invert this operator, which is product of the three. Now, knowing that we can invert Hilbert transform on LP, where P is less than 2, not equal to 2, but less than 2, at least it's a Fredholm operator. So we can rewrite this operator in terms of the finite Hilbert transform applied to this operator S, which has a known symbol, plus something else, and the something else is going to be smooth, okay? So you see that we are going in the direction of invertibility plus smoothness. So as long as we know that this finite Hilbert, whatever transform, it's continuously invertible on its range for P between 1 and 2, because otherwise we know that it's not true, then this trace condition that I postulated will hold, okay? What do we know about this operator S that is somehow part of the block? It's an operator that loses one, its inverse loses 1/2 derivative. That's why we'll have a 1/2 minus epsilon, the final result. And this can be shown by calculation of the symbol. So we can do this. So if we go back to our equation, which can be written that D is given, it's exactly coming from the structure. And here we have this finite Hilbert transform applied to this operator S, which is losing derivative. This is just restriction on element psi that I'm looking for. And this is plus something else. And I want to claim that this is compact. And why is this? Because you are looking at the support of that symbol. Okay? Because psi is 0 outside omega, one can show that singular support of this operator here, which is V, it's exactly this, it's also empty. Okay? So therefore, V is compact. So we are having some invertible plus compact. And now working with a Sobolev embedding, which is pretty standard, and embedding this LP theory, we end up exactly that our elastic potential, it's in -1/2 minus epsilon, and that allows us to provide original solution to the problem. Okay. Now, here I ran out of time. I had slides about long time behavior for that model. So probably another time, but all the results were stated at the beginning, and we can prove by using also some of this techniques, but what was really important to understand the Skuta-Yukowski boundary conditions. And I'm going to stop here. Don't want to take more of your time. So this I will not be able to finish. So perhaps I go to the conclusion. We show the stabilizing effect on the flow is exhibited only for a correct model, which does not have rotational inertia. So we have to be careful with mathematics by throwing in terms. And nonlinearity of the structure is critical for the result to hold. Okay, so this is work in progress. Of course, what we would like to do, would like to take a nonlinear flow equation, Navier-Stokes, because capital U comes exactly from vorticity. So these can be pretty large things. Okay, so one first step going to nonlinearity is to accept some viscosity. But still, the situation is not very well understood. And of course, we would like also to consider transonic case, but one has to consider nonlinearity of the flow, because in transonic case, you have degeneracy of elliptic part of the problem. And we are still working with Gazola and Bonner on learning more about the attractor for the structure by doing also a lot of numerical calculations. Okay. So I have some of the, thank you very much for your attention. And I apologize for taking more time.
Professor Irena, thank you very much for an interesting lecture. Thank you very much again for your lecture.
Thank you. Thank you for your attention.